Thank you everyone for coming. Sorry for the hiccup. So today we're going to talk about using neural networks for time series prediction. So to give an outline of this talk, just in general, this talk is actually going through a particular problem that I wanted to solve and how I use neural networks to solve this problem. Don't see this content as the canonical source of truth for how to use neural networks to solve a problem. This is just how I use neural networks to solve a problem. So to begin, we're going to introduce the problem that we wanted to solve. You want to remember what you're actually trying to do, not just how we're doing it. Then we're going to talk about phrasing this kind of business problem, or not business problem, as a machine learning problem. Then we're going to collect and apply data to solve our problem. We're going to go over how we selected features from our data to answer the questions we want to answer. Then how we concretely train the model. Finally, some improvements we made to the model and some general tips and problems that I encountered along the way. So to give you some context, I work at a company called Quantopian. We build tools for people to do quantitative finance. We have things like hosted Jupyter notebooks and a simulator for running strategies over historical data. I mostly focus on working with time series data and integrating new time series data in the platform. So I've seen all kinds of things like market data, sentiment data, earnings estimates, satellite image data, you name it. I've looked at a lot of really interesting time series data. But today we're going to talk about my personal favorite time series. So we're going to talk about a video game called OS. OS is a rhythm game where you click circles to the rhythm of music. The game is pretty simple. You have circles where you click with your mouse. You have sliders where you click and drag along the path of the slider. And then you have your mouse cursor itself. The way the game works is you score 300 points for clicking a circle exactly on the beat. You score 100 points if you're slightly off the beat, and the game will display a little notification that you are off the beat. You score 50 points if you're really off the beat, like by more than a 16th note, and you will see another indication telling you that. Finally, if you don't click the circle or you click with almost no regard for rhythm, then you're going to get a miss, and the game shows a little X. So I could try to explain how it works, but I'm just going to show you a little video of the game itself. And there's no sound. Imagine there's your favorite anime music playing to this because it's all Japanese songs. So this is an example of the game on a slower difficulty or an easier difficulty. And the next clip is the game on a difficulty that I would normally play at.
Let them out.
Yeah, so the game speeds up a lot. Great. So to phrase the actual problem, what I wanted to do was improve my rank very quickly. So the game gives you points depending on how well you do on songs and how hard they are. There are many new songs that are being made every week. It's an open source game, and there's a large community of people who actually create the songs and the layout of the circles. Importantly, though, the songs are of varied difficulties. And different players have different play styles. So I have a particular play style, and I find some songs harder or easier than other songs, even if the game objectively ranks them a certain way. So this presents an arbitrage opportunity where I can try to find songs that I will do better on that are ranked harder. So to phrase this as a machine learning problem, what I want to do is predict my score on a given beat map. So to do that, we need to compute the accuracy percentage, which breaks down to the temporal accuracy, so how on rhythm I am, and whether I will click the circles or not. So to give an overview of machine learning models in general, machine learning models mostly fall into two categories. We have classifiers, which take a sample and label it as a member of one of a finite set of classes. So this is useful for things like image classification, where given an image, you want to know, is this a picture of a dog or a cat or the number 1? And you know what all of your classes are ahead of time. You also have regressors, which approximate an arbitrary numeric function, which are much more general. So at this point, and then since this is about time series data, we have LSTM models, which is a type of time series neural network, which allows you to model order-dependent data. These mostly model an idea of a sequence of observations. And the way that these use the time aspect is you train on, instead of a single sample, you give it a window of time-sorted observations. So to phrase our problem as one of either a classifier or a neural network, or a regressor, sorry, we could try using a classifier where we would label every circle in a song. So for every single hit object, which is a time series itself, we would label it as a 300, a 100, a 50, or a miss. The other option would be to use a regressor, where we would predict some type of error metric. Here I've talked about aim error, which is the XY error, so where you are clicking on the screen, and the accuracy error, which is your punctuality or the temporal error in the song. At this point, I didn't actually know which to use, so I decided I would go look at the empirical data that I've collected. So the first piece of data we have is a beat map. So this is where all the circles are paired with the song itself. So we have all our hit objects, the circles and sliders, and they're in XY time space. So you can think of this as a big 3D array. We also have some scalar values associated with every song. We have the circle size, which is how many pixels a circle is on the screen. We have the approach rate, which is the time between a circle appearing on the screen and you needing to click it to achieve the correct score. And there's also the overall difficulty, which is the width of the thresholds. So this is how many milliseconds away from the beat can you be before you score a 100 or a 50. And those are different in different songs. Looking at our raw data, we see it's just kind of a text file with a bunch of coordinates and information, and it's not super structured. It's not just like pd.read CSV or something. There's also modifiers. So you can play if you find that a song is too easy, you can make it harder by making all the circles smaller or flipping the map using hard rock. There's also double time, which doubles the speed of the song. This is used in the second example, as well as hidden, which makes the circles disappear before you have to click them. So they appear on the screen, then they disappear, then you click them. That was also used in the second example. And there are a couple others that change the way that the game is played. We also have replay data. So the reason that I could actually do this was that the game records a replay every time you play, which is a time series of your cursor location as well as the keyboard state. So it's just a bit mask of what keys are being pressed. You don't actually click with your mouse. Normally, you click with the keyboard. You press a key on the keyboard. Also, I have about 7 years of replays, so I have a large enough data set that I can actually do some machine learning here. So to understand a little bit more about our data, I mentioned that one of the metrics was the overall difficulty. So this is a table showing how many milliseconds it takes to score a 300. So you'll notice on the hardest difficulty, you have 19.5 milliseconds to score a 300. The problem that this presents is that any given 300 is not directly comparable to another 300, or 100 is not directly comparable to any other 100. So if I wanted to use a classifier on this model, just labeling something as a 300 isn't exactly enough, because on an easy song, you should get more 300s, even for the same error. Also, looking through my replay data, this is the distributions of the scores. So I'm pretty good at the game, so I mostly just score 300s and not 100s or 50s. So the classes are extremely biased. So if I wanted to train a classifier on this, it doesn't actually see a lot of examples of 100s or 50s or misses. So I went ahead and tried to use a regressor. So I needed to actually get the metrics that I was talking about. So to join the data, I find all the clicks by taking the times when the keyboard state changes. And then I match the click temporally with the nearest hit object. An important thing is this ignores a feature of the game called hit locking. It's not important to know what that is. It's just that this is a simplification of the way the game is played. This is not actually how you would resolve whether you clicked a circle or not, but it's good enough. And we can make these kinds of simplifications for the sake of modeling the game. So to get the accuracy error, I just take the absolute difference in time. And the nice thing about this is that it eliminates the overall difficulty metric from the game. I'm just going to predict the error in the click, and I don't know yet what that score would be, and that's okay. So we don't need to model that feature. For the aim error, I just take the distance between where I click and the center of the circle. Again, this is nice because I can compare the error across different circle sizes. I don't know whether I hit or not, just what the error is. Now we have to extract some features. So what is a feature? A feature is the numeric inputs that you feed into your model. So I said that a regressor is approximating a numeric function. It can't just take whatever. I actually have to give it some numbers. So for our LSTM models, this is really what we are observing. So I said it's a sequence of observations. What is an observation? Those are your features. This allows us also to focus our model on important aspects of our data. And this is where we get to use our domain knowledge. So to revisit, this is what a beat map looks like. It has some structure, actually has a lot of structure, but it's not immediately obvious. So one option would be to try to just feed a neural network like a big text blob and try to learn something from it. I think in theory that should work, but we know a lot more information about what is in this text. We know, so looking at the first row, this says that we have a circle at, actually we have a slider at 103, 272, 52,000 milliseconds into the song. It's a linear slider that goes from that first coordinate to 111 by 176. So there's a lot of important structure here, and it would take a long time to learn it. So instead, we can just extract that. And instead of feeding it the text blob, we're going to feed it an array of numbers. So some simple features that we can extract from these beatmap files are the absolute x, y, and time for every hit object. I also said that this was a chance to use some domain knowledge. So one domain-specific feature that I've used is the angle through a circle that you click. So here, if we have 3 circles in order of 1, 2, and 3, I would label circle 2 with this angle here. And I believe that this has some effect on whether I can click this circle, because it is literally how fast I have to change the direction with my cursor. One interesting thing, though, is that I can't exactly explain how the angle affects my ability to click this circle, but I believe it has some effect. And more importantly, I actually believe it has an effect on my ability to click the next circle. So I think the angle of 2 more directly affects my score on circle 3 than on circle 2. But because we are using a time series model, the LSTM model, the sequence of observations will be learned, so we can actually have the order of those angles get some information for us. So I also said that we're not just going to train on a sequence of observation, but little time windows. So here's a table of some circles from a song with their time and x and y coordinates. So to construct these windows, what we're going to do is select one row of observations and then draw some context around that. So here I'm saying that we are going to look at the leading 4 circles and then the following 2 circles. In most models, if you ever wanted to do real-time predictions, you would not be able to look at the following data because you don't have it yet. But here, I already have all my data ahead of time, so I can look at the circles that come after it. Also, in the game, you can see the circles before you're supposed to click them. So I believe that the circles that follow the one I'm trying to click are much more important in determining whether I will click the one I'm trying to click now. That makes some sense. So once we've drawn this window, we can actually generate some new features where we take relative offsets from the row we're trying to predict for and all of the other values in our time window. So here, what this is saying is we've drawn a little window of observations, and we're going to take the difference in the x coordinate and the difference in the y coordinate from the center of our window and all of the other observations. What this is doing is it's telling the model that not only is the absolute position on the screen important, but it is the distance between all of the objects that's important. And then you just slide this window through the entire song and generate a bunch of little windows. You might be thinking, can all this information be learned just from the absolute positions? Because the model could theoretically learn the differences are what is important. And that's true, but this goes back to focusing the model. So it takes a really long time to train this already. I want to make it a little faster, and I'm saying these differences are important. You should focus on those. This is just a list of all the features I have. One thing to note is you don't need to make relative versions of all of your features. I don't actually care about the relative angles. I just care about the absolute angles through all the circles, for example. All right, so we've talked about the inputs. Now we actually need to train this thing. So we need to generate a big numeric array of all of the data we want to feed to our model. So the feature arrays, or the inputs to our model, is going to be a 3D array. The first thing we have is the number of features. So this would be all of that big list before. So this is for each single scalar observation by the window length. So then we have our windows of observations. Finally, by the number of windows that we have. So this is a sequence of little time windows through our songs. And then we have to label our data. So we're going to have two parallel arrays, which are just 1D arrays, which is the length of the number of windows. And these are going to be our two error metrics. And you might be thinking, couldn't this just be a number of windows by 2 array? But there's actually a good reason to split them, which I'll cover in a second. So we're going to use Keras for our actual training. Keras is an amazing library. It's built on top of TensorFlow for doing neural network stuff. So to start, you create an input node in your computation graph. And what this says is that the shape of our inputs are window length by len features, or number of features. You might note that this does not have the number of observations. So this is saying, what is the shape of a single observation? Next, we're going to just use Keras's LSTM implementation. This is the magic part. You don't need to write this or learn how the LSTM works. You can just use it, and it's implemented very well. So to do that, we just say how many neurons we want in our LSTM node, and we feed it the input. The way you figure out how many neurons you want is through trial and error and asking your friends and coworkers. I don't know the answer to that. Next, we're going to define the outputs of our model. We're going to start with our aim error, and this is going to be a Keras dense node with 1 value. That's what the 1 there is. And you pick some activation function. You also do that by asking your friends and coworkers. And here we can name it. So we're going to call this node the aim error. And we feed that the previous node in the graph, which is the LSTM. And then we're going to do the same thing for our accuracy error. So again, you might think, couldn't I just predict like a tuple instead of 2 scalar values? But one nice feature of Keras is that if you split them up like this, you can name them separately. And then when you're training, you get to see the loss or the how poorly the model is predicting these things for each different value. So you get to just name them, and it makes everything look a little nicer. We then need to just throw this graph into a model object where we specify our inputs as the input object and our 2 outputs as the 2 error metrics. Then you compile it, and picking those parameters is the same as before. To actually fit the model, you feed it your features array, which was that number of windows by window length by number of features array. And then we pass a dictionary with our 2 parallel arrays of our error metrics. So I went and trained this model. Oh, and then to predict, you give it an array the same shape as your input, and it will spit out the 2 scalar values that we've named. So I went and trained this. I want to evaluate it, and it just looked terrible. So at first, it just was predicting basically random noise. And I didn't understand why, so I talked to some people, and they told me that neural networks are extremely sensitive to the input ranges. So you can't just be giving it arbitrary numeric values. You need to center them, and they need to have a standard deviation of 1. So to do that, you take your feature array, and you subtract out the mean, and you divide through by the standard deviation. You want to do this column-wise, so this is for every single feature you do this. A very important thing, you need to save the mean and standard deviation of the training data, because when you take the data you want to predict with, you need to subtract out the mean of your training data and divide through by the standard deviation of your training data, not of the data you're predicting with. So I went and scaled it, and it was still terrible. It was just predicting random noise. So I looked at the raw data that I had. And so these are some features, the absolute X and absolute Y. Mean looks good for both of them, but it appeared that I had some outliers. So the thing to know is that the OS playfield, the actual screen size, is 512 by 384. So those maxes didn't seem right. So actually dive into this one. So this is a picture from the game editor, which is the tool used to make the maps. This is a slider. Zooming in on this slider, you'll see there's a bunch of little points there. This is supposed to be a piecewise linear function that connects all those points. But this map is 10 years old, and they've changed the data format. So I accidentally was interpreting this as a Bezier curve with all of those as control points. So using Matplotlib, I can plot the expected path, which looks like the thing we saw in the game. But I was interpreting that as a really high-order Bezier curve, which looks like this. And if we zoom out to show how long that tail is, it's pretty big. The interesting thing about this was that it was not just a problem. It was not a problem how I was using Keras. All of that seemed to be correct. And I spent a lot of time thinking I was using Keras incorrectly. But really, it was a problem in my data collection pipeline. It was like, this was a problem because I had a 10-year-old file and my open source parser for this didn't work. Not that I was like using ML wrong, but if your data is garbage, your ML stuff doesn't work. So kind of circling back to the original problem, I wanted to predict my accuracy. And I've just got these two error metrics now. So we need to discretize our scores. But these score thresholds are pretty big windows. And if my model says, I think you're gonna click with 19.4 milliseconds of error, and the song is OD10. Well, if I just said, OK, I'm going to score that as 300, that's not actually capturing that I was right on that boundary. And the difference between a 300 and a 100 dramatically affects the accuracy that you'll achieve. So I wanted something that would capture the boundary, like how close you were to the boundaries. So I looked at the data that I had, and this is the distribution of the aim errors in all of my replays for the last 2 years. Other than an outlier up by 70, it looks like a pretty good log normal distribution. Then the temporal accuracy, I did the same thing. There are these spikes, and they're not actually binning errors. This is because there's more errors that are multiples of the milliseconds of the BPMs of the songs that I play. So there is actually some regularity to that error, but I said it was close enough to a log normal. So what I decided to do was take my predictions and actually fit a log normal distribution to them, and then take the expected value of all of my predictions instead of taking the scalars. So I think this code's kind of cool, so I wanted to go through it. So the way this works is, can people read this in the back? Cool. Almost. I don't know how to make it bigger really quickly, sorry. So what I do is I predict the differences. So the first line is using Keras to actually predict the two parallel arrays, which are the two error metrics for every circle. We then fit each of those. So for all the circles, we fit them to a distribution for the whole song. To take whether I'm going to click or not, it is the cumulative distribution function at the radius of the circles. So it's the area under the error distribution before the circle radius. And then to compute the expected value for the temporal accuracy, this is an ASCII art picture of a probability density function, which I put in my code because I have a visual intuition for how this works. And I know I'm going to forget this if I don't have this picture. You can just take a weighted sum of the areas, and that gives you the expected value of the temporal accuracy, and then you just multiply them together, and now you have the expected score on a song. So I was running this for a while, and it was making predictions that assumed I was really good at the game. So I liked the structure. The errors that it was predicting were things that I thought would be harder. There was interesting structure in how the errors were, but the magnitudes were too low. So looking again at the distribution of the errors that I have empirically, they're mostly really small. So maybe it's hard to have an intuition for how big the circles are, but 19.5 milliseconds was the threshold for 300 on the hardest difficulty. So from the histogram, we noticed there was a lot of 300s. So I was much more interested in the outlier conditions, or the notes that were going to be predicted to be hard than notes that were predicted to be easy. So I wanted to tell my model to focus more attention on the difficult notes than on the easy notes. And to do that, we can use Keras to weigh each sample for each different error. So what I did was I said that anything that was 1 standard deviation above the mean or below would be weighed at 1/4. And then anything that was 4 standard deviations or above would be weighed at 1, and then just a linear scale between them. So what this does is it says that all of my outlier conditions are more important than all of the regular data that I saw. And this actually made the model make slightly better predictions. So now to look at some out-of-sample data, what I did was I downloaded a new song that I never played before, played it a couple times, and then asked what my prediction would be. So for the first play, this is what the plot looks like. Second play, you'll notice I scored a 50 at the end there on a note. And then the third playthrough. Then this is what the predictions are. So you'll notice that the charts aren't exactly the same, but one thing to know is that I fed the same songs many times into my model with very different scores because I play songs more than once, which is why I did the expected value thing. But it does identify that second high peak at the back right there is the same note that I scored a 50 on. And I scored a 100 on it in almost all of my plays. So it is actually picking out some interesting features of the songs. But the real thing I wanted this for was to arbitrage the game score mechanism. So the far right column here is the game score. The left column is my prediction, and then the right is my actual. So the first three are the 3 songs plays that I showed the charts of. So my actual and the prediction is really close. Again, the percentages have pretty large jumps because the scores are discretized from 300, 100, or 50. But then the last two are interesting. The song is harder, and it predicts a lower score than the first song, and I do score lower. But the final row is even harder than the previous one, and my model predicts I will do better on it, and then empirically I do. So I am finding some difference in how I play from the way the game scores, so that I count that as a success. Some general tips, which I'll go through quickly because I think I only have 3 minutes. Use verbose flags to log information as you're going, but make it optional, because if you actually want to deploy this, you probably don't want to print after every single line, but training some of these models and cleaning your data can take a long time. So you want to have some insight into where you are in the pipeline. For progress indicators like scikit-learn or Keras have, when you're training, you can use click.progressbar to build your own. And print summary statistics as early as possible in your processes. I would have saved a lot of time if I had just printed the outliers of my data instead of training multiple times on basically garbage. Software engineering still matters. So one thing I found really helpful is to group all my models into domain-specific objects, which handle things like feature extraction, scaling, label extraction, and managing the Keras model. This lets me change the implementation of my model later and not have to fix everything else. It's not just 100 functions scattered around. I just call fit and predict, and it takes domain objects and returns domain values. And this also facilitates serialization. So a really interesting thing you can do with your models is save them. So this allows you to do things like training on EC2 and then sending the results back to you to use locally, or going the other way where you train on one machine and then send the pre-fit model to another machine to actually deploy. This is a feature that's supported by Keras. So all you need to do is wrap up all of your domain-specific stuff, and then you can delegate serialization to Keras so that you can save everything together. Some key points. So if you only remember stuff, remember these. Most of the work is going to be done before you get to Keras. I thought for a long time I hadn't actually done ML even when I had a website running where people could upload data and I would train models for them, like it's actually all the data cleaning before Keras. Keras is so good that you won't spend a lot of time using it. And that's a testament to how good Keras is, not that you are not doing machine learning. And then more importantly, understand your data and the data collection process. It's not just what data you have, but how did you get that data? Because you might find like biases in the data, like all of my clicks are 300s, and that's just how the data is being collected. That's not a problem with the data itself. And finally, OS is a really fun game. You should play it. Thank you. So all of the code I showed. So the model itself, how I implemented it is on GitHub under my GitHub, which is 10 lowercase l's /lane. The tools for actually parsing all of the data and creating the arrays and stuff is Slider, and then Combine is a service that runs a website and an IRC bot where you can train your own model. And you can message my account in the game to get predictions.
And Joe, are you also on Twitter or social media?
I'm on Twitter, under qual name.
Okay.
Yes.
All right. We have a couple of minutes for questions. Does anybody have a question in the audience that would like Joe to take?
Yes.
Hold on. Mike. You are being recorded.
Noted. Well then, why neural networks? Why not random forests or any other machine learning model? As you said, a lot of the value you're providing is in the feature engineering. So this is probably a learning exercise, but do you have any thoughts onto why this particular problem would be better suited or worse suited for neural networks?
Yep. So I actually tried using a different kind of model. I was using, I tried actually like a bunch of different things in scikit-learn, like a large suite of things, but I wanted something that took the temporal aspect of the circles into account. I'm sure there's probably a way to do that with other models, but this was just the one I tried.
Hi. Just out of curiosity, using LTSM, did you try this with the softmax layer? And were you able to see kind of which predictions were more or less accurate, just to get a feel for how they felt, like with that extra layer at the bottom?
No, I did not. But I would love to talk to you afterwards about that. I'm not really a machine learning expert, so I kind of just tried most of the Keras stuff out of the box. So if people have tips for more advanced machine learning stuff.
I'm sure a lot of people want to ask, and I'm not sure if you mentioned that, how long actually that took you from kind of starting with the model to actually perfecting it? Because I think that's what everybody's on everybody's mind, what that sort of period of time.
Yeah. So the project in total probably took like 5 months, maybe more, maybe like 6 or 7. A large part of that was writing the lower level tools to like parse the files and parse the replays and compute scores and things like that. The model itself probably took like 2 months of work, but this was all like on free time. So most of that was like researching stuff and talking to people and trying to find when people are available. So
how much, and I think you mentioned that, but how much, sort of emphasis you would take that actually being able to communicate and ask questions, with the right people?
Yeah, one of the most important things for this was being able to talk to like my roommates and coworkers and people who knew various parts of it or different things, and like that's a great resource for people.
Thank you.
Any more questions? Oh, in the back. This will be our last question. Sorry. Come in.
Yeah, hi, thanks for the talk. I was just wondering, with neural networks for time series, there's this question of stationarity, right? I mean, I imagine your skill changed.
Yeah.
It probably plateaued at some point, right? So
Plateaued.
was some high percentage of your data, well, maybe you're still growing. But most of it, it was like sigmoid or something. So if you cut out the really early data, would this improve your predictions, kind of thing?
Yeah, that's actually a great point. So I actually throw away everything but the last like 6 months of data because I'm not plateauing. I'm getting better every day. So yeah, so when I trained with all of the data, it would be like the same song, but I'm scoring like terribly on it. And then now, like yesterday, I play it and perfect score. So the model was not really learning anything interesting because it didn't know like how that was affected. One way I think you can still use some of that data is you can use the weighing again. So you can weigh samples that are older as less important and weigh newer samples more. I didn't look into that. I just throw away everything but the last 6 months because I play this game a lot. So that was still enough data. Thank you.
Thank you, everybody.